Welcome to this lesson on cloud provider integration in Kubernetes. In this video, we'll explore how Kubernetes seamlessly connects with cloud platforms to provide powerful features like external load balancers and persistent storage. Understanding cloud provider integration is essential for running production workloads in modern cloud environments. Let's dive in and see how Kubernetes bridges the gap between your applications and cloud infrastructure. The Cloud Controller Manager, often abbreviated as CCM, is the key component that bridges Kubernetes with cloud provider APIs. Think of it as a translator that allows Kubernetes to communicate with your cloud platform. It manages cloud-specific control loops that handle tasks unique to each cloud provider. The Cloud Controller Manager enables load balancer services by provisioning actual load balancers in your cloud account. It also handles node lifecycle management, keeping track of which nodes are healthy and available. Additionally, it provides dynamic storage provisioning, automatically creating storage volumes when your applications need them. To expose an application externally in Kubernetes, you can use the load balancer service type. Here's a simple example manifest. You start by defining a service with a PI version v1 and kind service. In the metadata, you give it a name like my dash service. Under the spec section, you set the type to load balancer. Then you define the ports, specifying port 80 as the external port and target port 8080 as the port your application listens on inside the pod. When you apply this manifest, Kubernetes instructs the Cloud Controller Manager to provision an actual load balancer in your cloud environment. Let's walk through how the load balancer service works step by step. First, you create a service with type load balancer using your manifest file. Second, the Cloud Controller Manager detects this new service and recognizes that it needs a cloud load balancer. Third, the Cloud Controller Manager makes an API call to your cloud provider to provision an actual load balancer resource. Finally, once the load balancer is created, an external IP address is assigned to your service, and traffic from the internet is automatically routed to your pods. This entire process happens automatically, making it easy to expose applications to external users. Different cloud providers offer their own load balancing solutions that integrate with Kubernetes. On Amazon Web Services or AWS, the Cloud Controller Manager provisions an elastic load balancer, commonly known as ELB on Microsoft Azure. It creates an Azure load balancer that distributes traffic across your cluster. On Google Cloud Platform, abbreviated as GCP, it uses cloud load balancing to handle incoming requests. Each of these load balancers is fully managed by the cloud provider and seamlessly integrates with your Kubernetes services, providing high availability and scalability for your applications. Persistent volumes, or PVs, provide a storage abstraction that is independent of pod lifecycle. This means your data persists even when pods are deleted or restarted. Persistent volumes survive pod restarts and deletions, ensuring your data remains safe. They are backed by cloud storage services like Amazon EBS, Azure Disks, or Google Persistent Disks. Kubernetes supports dynamic provisioning, which automatically creates storage volumes when needed. Persistent volumes also support multiple access modes, allowing you to configure whether storage can be mounted by one node or multiple nodes, and whether it's read-only or read-write. Storage classes define how storage should be dynamically provisioned in Kubernetes. Here's an example of a storage class manifest. You begin with a PI version storage.k8s.io/v1 and kind storage class. In the metadata, you give it a descriptive name like fast-storage. The provisioner field specifies where the storage comes from. In this example, we're using kubernetes.io/os-ebs, which provisions Amazon EBS volumes. Under parameters, you can specify the type of storage, such as GP3 for general-purpose SSD storage, and set performance characteristics like IOPS per gigabyte to 10. Storage classes make it easy to offer different tiers of storage for different application needs. Dynamic provisioning automates the creation of storage volumes. Here's how it works. First, you create a persistent volume claim, or PVC, that references a storage class. The PVC describes what kind of storage you need, including size and access mode. Second, the storage provisioner defined in the storage class creates the actual cloud storage resource, such as an EBS volume or Azure disk. Third, Kubernetes automatically creates a persistent volume object that represents this cloud storage. Finally, the PVC is bound to the PV, and the storage is mounted to your pod, making it available for your application to use. This entire process happens automatically without manual intervention. Each major cloud provider offers multiple storage options that can be used with Kubernetes. On Amazon Web Services, you can use EBS for block storage, EFS for shared file systems, and FSX for high-performance file systems like Lustre or Windows File Server. On Microsoft Azure, options include Azure Disk for block storage, Azure Files for shared storage accessible via SMB protocol, and Azure Blob for object storage. On Google Cloud Platform, you have Persistent Disk for block storage and FileStore for managed NFS file shares. Each storage type has different performance characteristics and use cases, allowing you to choose the right storage for your application needs. Let's recap the key points from this lesson. The Cloud Controller Manager is the component that enables cloud integration, acting as the bridge between Kubernetes and your cloud providers. API load balancer services automatically provision external load balancers in your cloud environment, making it easy to expose applications to the internet. Storage classes enable dynamic volume provisioning, automatically creating persistent storage when your applications request it. Finally, each cloud provider offers unique storage options with different performance and feature sets, giving you flexibility in choosing the right storage solution. Understanding these cloud integration features is essential for running production Kubernetes workloads in cloud environments.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.